The Van de Graaff generator is a really helpful tool that we can use for static electricity. Van de Graaff generators have a belt with rubber, and they're going along this belt, and there's some metal teeth that's connected to a sphere. And as this rubber goes against these teeth here, it pulls electrons off of the sphere and then pulls it onto the belt, and then that belt transfers the electrons to the wand. So the wand becomes negatively charged, and the metal sphere becomes positively charged. And it's a nice, easy way to be able to get charge from or develop charge from a conductor, and use it for static electricity experiments. All right, now we're ready to talk about electrical force. And so, you've seen from, very, very early on how charges, exert force on each other. Like charges repel. If we had two positive charges, they're going to want to push away from each other. And then likewise with opposite charges, if we have one that's negatively charged, one that's positively charged, they're going to be attracted to each other. And so like charges attract, opposite charges repel, and that governs our thoughts with forces. And Coulomb's torsion balance is the device that they used, and it looks very, very similar actually to Cavendish's experiment with the force of gravitation, and really operates on a similar principle. So if we look at the force of gravitation, right, it's dependent upon the two masses and the radius between them, and we have the gravitational constant g. And then, with the Coulomb's torsion balance, you had two charged objects over a certain radius, and there's a certain amount of force. To further explain the Tolman-Stewart experiment, I added this last year, and I'll have you guys read this real quick on the practically, like how they actually did this experiment. So go ahead and pause the clip and read through this, and you can see how they did that here. Okay, so the galvanometer, and that's something that you made. That's an ammeter. It'll show you how much current is going through, how much charge in a period of time is going through. It's very, very sensitive. All right, so in class I show quite a few visuals with this. The force is directly proportional to the charge and inversely squared to the radius. And so if you, let's say, have two charges, and let's say this is positively charged, this is positively charged. Let's say we doubled the charge on this one. That would mean that, if we calculate it, we have a force. K is the constant, Q1 is the first charge, Q2 is the second charge over R squared. It would be twice as much Q1 if we call this charge 1. Therefore, it would be twice as much force. However, with distance, let's say this is 1 meter, and we stretch this to 2 meters. This is over R squared. So it's actually reverse exponential, that relationship. If we doubled the distance, we'd only have 1/4 of the force because it's radius squared. This is one way to write Coulomb's law. We have Q1, Q2 over R squared. We have the two charges. And this is K, 1 over 4 pi epsilon naught. Epsilon naught is the constant for the electrical force within a vacuum, and typically we assume that these objects are in a vacuum. They work very similarly in air, and we can figure out the force. More commonly, what we actually use is if we had a different medium, we'd use a different value for the permittivity there. This is how it's more commonly seen, though. Forces in newtons. K is that value, that 1 over 4 pi epsilon naught that you just saw. Q1, Q2 are the charges in coulombs, and then R is the distance between them. So we'll work through some examples here and practice that. And then Coulomb's law only applies to spherically symmetrical charges, and so only spheres, and so it's important to remember that. Coulomb is, had a huge influence on our understanding of electricity, and it's important to, talk about his works. The way that they published, and he was born in 1736 and died in 1806. He published his findings in actual books called memories, and so today we publish things in publications, but the way that they published back then were actually in books. Okay, so let's go ahead and try this one here. Let's say we have a positive charge, 12 microcoulomb charges, and experiences an attractive force, 51 millinewtons. It's placed 15 centimeters from the other charge, and we want to figure out what the other charge is. And so we know we're going to have to convert our charge into coulombs, and our length is going to need to be in meters, so we'll need to do that. Force will need to be in newtons. And we can see what the other charge is. And so if you want to go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so Q1 is 12 times 10 to the negative 6 coulombs. The force, 51 times 10 to the negative 3rd newtons. And then we're looking for Q2. We know the radius between them is 0.15 meters. And so if it's an attractive force, right, this is being attracted, this must be negatively charged, right, because opposite charges attract. And we should get negative 1.064 times 10 to the negative 8 coulombs. All right, so let's say we have this situation where we have a charge that's on a pole hanging in the air, and then we have another charge that's suspended below it, just suspended in air. And we want to calculate what the mass is of ball B. And so what you're going to have to do first is draw the forces on ball B, and then they're balanced, right? The ball B is not going up or going down, it's just suspended in midair, and you can figure out how much mass it has. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we have the force applied, or the force of attraction between ball B and ball A because of the electromagnetic force that we've been looking at with Coulomb's law. And then we have the force of gravity. If we set up the sum of the forces in the y, the positive force applied going up, negative force of gravity down, the force applied and force of gravity are balanced. And so those two forces have to be balanced, the force of gravity and the force of attraction, because of electromagnetic force. And so we have our charges, we have our K value, and the mass of this would be 4.07 times 10 to the negative 10th kilograms. That is the mass of that object. All right, so what would happen if we have more than one charge, being forced? What will happen is the principle of superposition. We looked at this with waves. If we had two waves at the same place at the same time, we would be able to, figure out what the resultant is. And it's a similar idea here. We look at the forces and their vectors. All forces are vectors. And we take a look at, all the forces involved and get the sum of them, in vector quantities, and then get the resultant. And we do the vector addition, we get the resultant there, and that's superposition. So let's say we have three charges. Let's say that the charge on the left is negative 3 coulombs, the middle charge is 2 microcoulombs, and the last charge is 4 microcoulombs, positive, and both those are positive. And we want to find out what is the force on the 4 microcoulomb charge. So the way that this works is you just basically pretend like one's not there, and then figure out what's going on. And so we're all on the same page. Let's go ahead and call the one on the left Q1, the one in the middle Q2, and the one on the right Q3. And again, what we want to find out is what is the force on the 4 microcoulomb charge. That's the only charge that we care about, and in terms of what happens to it. Now, you may be saying, well, these charges are just going to start blowing away or coming together, right away, and that's true, right? This is kind of suspended in air. As soon as you release these charges, they're going to fly everywhere, right? So just at this moment, we want to find out what is the force on that charge. And so what we're going to do, the first one, is we're going to find the force on charge 3 due to charge 2. The force on charge 3 due to charge 2. So basically what we're doing is we're saying this does not exist here. All we care about is how is this one, Q3, affected by this one. Well, if they're both positively charged, this one's going to be pushed to the right. So when we calculate this, K, Q3, Q2 over R squared, 2 and 3, we're going to get however many newtons to the right. Because Q3 is going to be pushed by Q2. Now you may say, well, isn't Q2 going to be pushed to the left? Sure, but we don't care about that. All we care about is what is the force on this charge. That's all that we want to focus on. So we'll end up getting 0.072 newtons to the right for that charge. That's how it's going to be forced. Now, the next thing that we do is we want to find out what is the force on charge 3 due to charge 1. So in the second one, we ignore the middle charge. We pretend that it's not there. And we ask, okay, if this is negatively charged, this is positively charged, how is Q3 going to be affected by Q1? Well, it's going to be pulled to the left, right? So when we calculate the force, it's going to be blank newtons to the left. Now you may say, well, isn't Q1 going to be pulled to the right? Sure, but we don't care about that. All we care about is what happens to that 4 microcoulomb charge. And so we get 0.027 newtons to the left for the force of that. So we can ask, okay, well, Q3 is going to be pushed by Q2 and then pulled by Q1. Which one's going to win? Well, this one's going to win. This has more force. But now this one is fighting this one. And so this force is going to take away from some of this. And so when we get the addition of them, we'll get a net force of 0.045 newtons to the right, and that's the superposition force between those two. All right, so in this one, we want to find out what is the force on the -3 microcoulomb charge, and that's all we want to find out. So let's go ahead and call the first one Q1, we'll call the next one Q2, the third one Q3. So I'm going to have you practice this one. Go ahead and pause the clip and do that same process where you ignore one, you do the other. I kind of wrote out the first one there already. But go ahead and give this a try. Pause the clip, give this a try, and when you're ready to check, you can hit play to continue. All right, so for this one, we want to find out what is the force on Q1, which is negatively charged, due to charge 2, which is positively charged. So this is positively charged, this is negatively charged. Well, Q1 is going to be attracted to Q2, right? So when we calculate the force, we're going to say blank newtons to the right, because Q1 is going to be pulled to the right because of Q2. Now again, you may say, well, isn't Q2 going to be pulled to the left? Sure, but all we care about now is what is the force on the -3 coulomb charge. So 0.054 newtons to the right would be the force that it experiences. The second step will be, what is the force on charge 1 due to charge 3? So we pretend like charge 2 is not there. Charge 3 is positively charged. Charge 1 is negatively charged. How's that charge going to be affected? Well, it's going to also be pulled to the right. Q1 is attracted to Q3, right? So for this one, or whatever we calculate, it's going to be blank newtons to the right. So that's 0.027 newtons. So when we add them up, they're both going to be to the right, and the superposition force will be 0.081 newtons to the right for Q1. All right, so for this last one, what is the charge, what's the force on Q2? And just so we're all having the same variables here, let's call the left one Q1 again, the middle one Q2, the right one Q3. I'm gonna have you work this one all the way through on your own. Let's see if you can do it. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so force on charge 2 due to charge 1, we're going to ignore charge 3 like it's not there. How is Q2, which is positively charged, affected by Q1? Q1 is negatively charged, right? So Q2 is going to be pulled to the left, so this is going to be blank newtons to the left is going to be that force. And then for charge 2 due to charge 3, both of these are positively charged. Q3 is going to push Q2 away, so that's going to be blank newtons to the left, 0.072 newtons. So both would be to the left. We add them up, and the superposition force would be 0.126 newtons left. Or if you just wanted to say negative 0.126 newtons, that's assigning the direction there, and that's good.